Hi, and welcome to 13.3 Wave Speed. Did you notice in the previous lessons that the waves were moving? So, how fast are they moving, right? What is their rate of change of displacement? This will be reminiscent of one of the first formulas we learned about speed and velocity. So, let's take a quick look at the notes. There is just a little bit more to it than that. So yeah, the wave speed is the velocity of the wave. But don't forget, wave speed is dependent on the medium that the wave travels through. So take a slinky. If the slinky isn't really that tight, like if you're not stretching it out that much, it's kind of loose, you put a wave in there and it's going to slowly move across the slinky. But if it's like a more tight slinky, you're stretching it out more, you're changing the medium that wave is going to travel through. And the tighter it is, when you put a wave into it, a wave pulse, the wave will go faster through the slinky that's tighter than the more loose slinky. So in our example, we used a slinky wave. So that's the medium that the wave is traveling through. But it could be air. It could be like sound waves. The sound waves could travel through air, water, even solids. So the medium that the wave is traveling through will change the speed of that wave. Same with electromagnetic waves. So electromagnetic waves or light can travel from the vacuum of space through our atmosphere, which is made of air. Maybe it goes into the ocean, and that light is traveling through different mediums. And it's actually going to slow down as it enters certain mediums, like it'll slow down from going from air to water. That water actually slows down the speed of light. You can't get faster than the speed of light in a vacuum, though, so that's like you probably heard before, the speed limit of the universe. Anyway, so that's an important point. The wave speed is dependent on the medium. So let's take it back to basics now. And what are the units for wave speed? What do you think they should be? I'm going to call it meters per second because that's our speed. All right, meters per second. And then what should the formula be? Well, formulas for speed is typically like v is equal to d over t. So let's start there. When we're talking about waves, and let's say we just want to talk about one wave, can you think about what is a wave equivalent of distance or displacement? Like the length of something measured in meters, that's distance. So we're going to use wavelength instead of a d. And for one wave to pass by, what time is that? It's a special time, right? What is the time for one wave to pass by? That's the period. So that's how the d turns into the wavelength. That's the length of the wave. And for one wave to pass by, what's the time for that? So you could change the velocity formula to lambda over capital T. And we also know that frequency is equal to the inverse of the period. And so we have a period in the denominator here and a period in the denominator over here. So you could actually replace the 1 over t with just an f. And that's how we get our wave speed equation, v is equal to f lambda. That's how they'll typically see it, because frequency is kind of like a wavy type of stuff, and wavelength is definitely a wavy type of stuff. So if you're talking about wave speed, they typically use v equals f lambda, because it's fancy and cool, and it's like a new spin on the similar idea. So let's do the worksheet. Shouldn't be too bad. We have our new equation, v is equal to f lambda now. And don't forget, v is equal to the lambda over the period. So sometimes we'll use that as well. So it says, if a wave is traveling at 60 meters per second, let's do the guess method. So good old guess method. Okay, it has a wavelength, that's lambda, of 15 meters. What is the frequency? Okay, so v is equal to f lambda. And then we could plug in 60 is equal to f times 15. And what's 60 divided by 15? We're going to go 4. What are the units for frequency? Did you forget? That really hurts when you forget the units for frequency. That hurts my feelings. Get it? Hurts. Very funny. Very funny. And nobody's around to argue with me that, yes, I am hilarious. Number 2, what is the wavelength of a sound wave with a frequency of 50 hertz? And they're telling you the speed of sound in air is 342 meters per second. well, we'll save that for Unit 14 when we talk about sound some more. There's a little bit more to that story, but we'll save that for another day. Let's keep it simple now. 50 hertz. The sound wave travels through air at 342 meters per second, and they're asking for the wavelength of that sound. Have you ever wondered how long is one wavelength of a sound wave? And by the way, frequency, well, we don't have to get to it. We'll save that for sound. Let's just keep it simple. Plug it in the formula, Nangle. Let's go. V is equal to F lambda. 342 is equal to 50 times the wavelength. So that wavelength is equal to 6.84 meters. Oh, that's pretty low. That's long. 6 meters, almost 7 meters long. I'm less than 2 meters tall. Am I? Yeah, I think. Yeah, I'm about like 1.8 meters tall. So this is more than 3 times as long as I am, as tall as I am. That's a long wavelength, and that's a pretty low frequency sound as well. All right, number 3, a sound wave in a steel rail. So now it's not air. The medium is different. It's steel. It's a solid. So we went from an air medium to a solid medium, or a gas medium to a solid medium. Do you think it's going to go faster, slower? Before it was 342 meters in air. Now we're talking about steel. So how fast is that going to be, right? So what is the speed of sound in steel? Curious. Predict. Do you think that the wave is going to move faster in steel or slower? So the frequency is 620 hertz, and the wavelength is 10.5 meters. So now we could do V equals F lambda. What is that velocity? 620 times 10.5. That's going to be a pretty high number. That's 6,510 meters per second. Compare that. So that's for steel. Compare that to air, only 342 meters per second. So the sound travels super fast in a solid compared to a gas. That might be that. Could you run faster through air or steel? Air, right? Because it's counterintuitive. You don't think you could travel through steel, but waves can. And we'll learn in Unit 14 that waves are longitudinal and all the molecules are kind of bumping into each other. So in a solid, if the molecules are closer together, they don't have to travel as far to bump into the next one, and you wind up with a faster wave. That's Unit 14, though. We're just doing V equals F lambda, keeping it simple. This is good building blocks for later stuff. So it says a distance of 5 centimeters separates successive crests of a periodic wave produced in a shallow tank of water. That's a fancy way to say the wavelength, because this is our wave of water, right? Water waves. Successive crests mean here's a crest. The successive crest is like the next crest. All right? It wouldn't be this one that they're talking about. They're not saying 5 centimeters here. No. Successive crests means from here to here. And we know that this is 5 centimeters. What is this length that we're talking about? From one point to the next successive point, in phase with that point? That's the wavelength, lambda. So they're being fancy, and they're telling you what the wavelength is. So lambda is equal to 5 centimeters. How many meters is that? Do you know how to convert? Centi? Centi's 2 spaces. Is it going to be 2 spaces to the right? 500 meters? Is 5 centimeters equal to 500 meters? No way, Mr. Nangle, you're crazy. So you got to move it 2 spaces to the left, 0.05 meters. And the crest, okay, so then the second sentence is telling you if a crest passes a point in the tank every this many seconds, 4 times 10 to the negative 1 second. It's just 0.4 seconds. Why don't they just write 0.4 seconds? Oh, because I wrote this. What is the speed of the wave? Okay, so if a crest passes the point, so that means that one cycle happens in 0.4 seconds. So what's the hidden information they're telling you there? That's the period. So that's the time for one cycle. That's the period of time for one cycle. 0.4 seconds, or 4 times 10 to the negative 1 seconds. So, kind of what we did in the beginning, we said, well, it's just v is equal to the distance over the time, the wavelength over the period. So we could use this formula. Or you could calculate f is equal to 1 over the period. So that's 4/10, so 10 over 4. Whatever that is. All right, let's calculate it. 2.5 hertz, duh. All right, but this is really, and then you could do v is equal to f lambda, because that's what we've been doing. We got brain lock on that. But don't forget, I'm going to do it this way. V is equal to the wavelength over the period, because those are the numbers that they give you. And I want to be lazy and do only one equation, not these two equations. Get that stuff out of here. That's so much work. We'll just do v equals lambda over t, because we're savvy physics people. And we know that what wave speed is really all about. It's just the distance over the time. So we got 0.05 divided by 0.4. And then you get 0.125 meters per second. Okay, wave speed. We got that under our belt. We're still just learning the vocab. We're learning the ropes about waves. Then again, in Unit 14 and 15, we're going to put this into practice, kind of like we did with the sound. All right, well, it's been raining for the last couple days, and the sun just came out. So I'm going to go for a nice walk. But keep in mind, even on the rainiest day, the sun's still above the clouds, even though you can't see it. And it'll come out eventually. So just keep your heads high, Tigers. Have a great day.